Okay, thank you so much. Okay, let's get started, and welcome, and thanks for joining me here in Amsterdam or my kitchen, depending on how do you want to see it. So as Nico mentioned, we will be discussing pattern matching in Python. This is a very fresh new feature in Python, so new that actually it's only in alpha releases. It hasn't been released, but it's going to be available in Python 3.10 in October. So before that, let me introduce myself a little bit. My name is Moisset. I'm originally from Argentina, but I'm living in London for the last 5 years. But yeah, I would love to actually be there. I've traveled a few times to Amsterdam. It's really nice. And I'm also one of the co-authors of the pattern matching, what we call it the PEP trilogy, because it's 3 different PEPs. Pattern matching started, I mean, there have been many discussions about this idea over time in the Python mailing lists. And in mid last year, I think it was May or June, some momentum started getting gathered again. And there was an initial PEP author, which was PEP 622, that we co-authored with 4 or 5 people, including a guy called Guido van Rossum, which you may have heard of him. He's Dutch. Yeah, there's a huge momentum in the community, and a lot of people doing really hard work for this. So I joined this group of people. This original PEP received a lot of feedback, so it required to do a lot of changes before getting to a stage that it can be actually approved. And something that we noticed is that when everything was in a single PEP, the feature is a pretty large change in the language. I mean, it's it introduces a lot of new concepts. So when presenting this, many people weren't sure to do with the PEP because it was hard to understand, and it was trying to do many things at the same time. It was a bit of a specification, a bit of an explanation. So we separated into 3 different PEPs. So you have PEP 6.3.6.4, which is a hard specification for language implementers. 6.35 explains why it's designed the way it is. And 6.36 is the tutorial. It's an educational document to explain it for new people that have never used it before, so people understand how it works in a general idea, not the detailed implementation. So as I mentioned, this is something that's available right now if you're willing to download a Python alpha version, and in October you should be able to have it. So if we actually, let me open this, you should see my terminal at this point. If I run Python 3.10, you can see that I can actually enter this, which doesn't look like usual Python code. And this actually does something rather than a syntax error, which was what happened in 3.10 alpha 5. So it's out, it's working. So if you want to play with it, you can just run it and try out the examples. So let's yeah. So let's take a bit of a look at what are the ideas behind the pattern matching. And pattern matching, some people may have heard about the first thing that is out when people hear pattern. Oh, it's like regular expressions and matching strings. And the term pattern matching has been used for strings, but in our case is what we call structural pattern matching. And we're talking about the structure of objects. And pattern matching is used to work with objects that are similar but not quite. So the first question that we may ask ourselves is what makes objects different? And we can think about all the tiny little things in my background here as small objects. And I could tell you, okay, which ones are the circles? Say, okay, you have this black circle over here and this one over here, but you also have this white circle over here, and the color doesn't matter, they're all circles. And you can say, okay, what are the white figures? And you say, okay, we have this white circle, but not this black circle, this white dot, and this white plus sign, and this very white, this very big white X are all white shapes. So we are trying to have different criteria to select or separate these different shapes in my screen. And we want to do something similar with objects. So we and this is actually a term we use in the design of pattern matching. We are trying to look at the shapes of objects. So we'll use the word shape quite liberally here, not like geometrical shape like we did later in this slide, but we'll see what the shape of an object is. So this is the problem we're dealing with. We want to recognize objects, different Python objects by their shape, and we want to make the user able to write code that does different things depending on the shape of the object. So if let me see if I can see the chat. So so the shape of an object is something that makes this object distinct to other ones, and you can think of any kind of Python objects. So if this works for me, and I know we have some lag, but I want to try this. Can you type in the audience what kind of characteristics of an object you think are part of its shape? I'll wait a few seconds so I get a couple of messages in. Okay. People are telling me the lag is like 10 seconds, so bear with me while we wait. I hope someone is typing anything. Okay. So, something are coming in. So someone is telling me about the dunder wrapper of an object. Yeah, well, that's something how you convert it to string. So people say concave, convex. That's more geometrical, and we're talking about data objects. So in that case, that doesn't apply. So people are saying it's attributes. That's a great answer. The size, their attributes, the methods. All of these are things that we can look at in an object. So we can look at the type of an object. Type is an essential. Yes, someone's just saying this or was saying this 10 seconds ago. So the type of an object is an essential part that you can recognize integers from strings are quite different, and the main difference, or the main thing that you see about the difference is that they have a different type. You can also have, for example, if you have sequences like lists or tuples, different lengths, we can consider like different shapes. If we have a mapping like a dictionary, which keys are present and which keys are missing. If we have an instance of any kind of object, which are the attributes that are there or not. So you see that many different things can be considered a shape. And even I may want to match things by more exact values. So, for example, when I want to select, I want to say, you know what, I'm interested in the white circle that's on the right side of my slide, and it's this one over here. And it's just as one, so I can match by exact value too. And to make it more complicated, when matching objects, I can start nesting these and combining one with the other. So this essentially provides me a way of, given an object that can take several shapes, I can figure out what think of shapes fitting holes, what hole this shape fits, and based on all of these criteria. And the first thing that you may think when I understand this is, oh, this is like a Boolean condition. This is like a predicate or something, a function that returns true and false on a given object. And this is the first confusion that people get when about pattern matching the way we presented it, is that, oh, it's a way of making nice if statements with nicer Boolean expressions. But there's an important insight that comes and that goes beyond saying if an object has a given shape or not, which is the Boolean yes/no answer that we're asking. But an important thing is that when we're writing code that cares about the shape of the objects, normally our code cares about the shape of the objects because we want to do something else with the object that depends on the shape. And typically what we want to do is to pull out some information from inside the object. So this is the key insight in pattern matching. When you're checking the shape of an object, what you want to do later on is extract data from it. So if you're checking if X is an instance of some type called DAC, it's because you probably want to call some DAC method on top of X. When you're checking on the length of an X, which is supposed to be a list, and you check that it has at least 2 elements, it's probably because you want to access to 2 of those elements. If you're checking that a key is in a dictionary, you want to access that key. If you're checking that an object has a certain attribute, it's because you want to access that attribute. So for many of these things, you have a condition, which is the Boolean expression on the left, but you also have some data extraction operation, which is the one in bold on the right, which is associated to that condition. And normally you want to do both things at the same time. And the idea of pattern matching is combining these two concepts into a single thing. So the key component of pattern matching will be our patterns. And the pattern will describe not just the shape of an object, but what kind of data inside the object we want to extract, what part of the object we are interested in. And we actually have something like that in Python, because we say, okay, we're designing patterns and we need some syntax where we can pull an object apart and get the little pieces and put them inside variables. And if you've ever used this syntax for this is called tuple unpacking, and I'm using the more advanced one where you can, for example, use this star in the middle to unpack multiple elements, you can essentially take apart a sequence, or actually any iterable in this case. And what we're telling here is put the first element into A, the last element into C, and everything in the middle into B with this assignment over here. So this feature is already there in older versions of Python, and it's very similar to what we want to achieve in pattern matching. And we're trying to we design pattern matching to follow many of these ideas. In many ways, pattern matching is taking this idea and cranking it up to 11, to max power, and see how far we can get with that. So as you can see, when I'm doing this, this is checking that the right-hand side is some sort of sequence of at least 2 elements. If I get the sequence that's too short, I'll get some sort of type error when running this code. So I have the conditional checking there. But this will also assign to some variables. And if you look at this, this is this syntax on the left. It looks like you can use this syntax A star B and C on the left assignment. You can also use it on the right or when passing parameters to a function or an if statement. But when it's on the left on the assignment, it has a different meaning, because on the left on the assignment, it's describing how to decompose a structure. Well, if you put it, if you put this in, for example, a print statement, and A is 1, B is a list with 3, 5, 7, and C is 9, you'll get this list back together. So you get the original list by using something like the assignment target that we used before. And this is something that's that we'll find in the syntax of pattern matching. We're describing some object decomposition, but the object decomposition, it or it mirrors the way we build a new object. So this code here is building a new object, building a new list. But this A star B C is not building a new list. It's actually unbuilding a list. So again, this is an idea which is already present in list unpacking, and we'll try to follow the same idea with pattern matching. So what we'd like to do is we will have these patterns on the left. And the question we are trying to ask is if the pattern of the left can generate the object on the right. We will call this object subject, and this is the terminology we use when pattern matching. We are matching a pattern with the subject and seeing if they fit each other. So the subject is my color piece, so like a particular plus sign, black plus sign on my right-hand side. And the pattern is a certain rule like saying all black objects. And essentially, the way we describe the pattern in Python is some bit of code, and we see if it can generate the code right. So the number 1 can generate the value 1 directly. That's what it does. So there's a match here. The value x can generate the value true. The thing that needs to happen for this generation to be successful is that x should be true. So in this case, matching this pattern with this subject will actually set x to true to make these two sides match each other. Can x match with a list like this? Yes, if x is set to the list 1, 2, 3, this will be a successful match. However, in this case, if we have a list of 2 elements x and y match, there's no value that I can set to x and y that make these things equal to each other. So in this case, the pattern of the left will not match the subject on the right. And you can match if the elements align, and the type doesn't matter, of course, because this is regular Python. X will get assigned to foo, and y will get assigned to 42 if I match these to each other. I get a successful match with 2 name bindings. X is assigned to foo and y to 42. And again, something like this is a valid pattern and can generate integral numbers, but it will never generate a number like this. So there's no value of x which will make int of x equal to 3.0. So that's what I'm saying here. It's not like the hard rule, but it's an intuitive context. So if you use it as a hard rule, you'll find that there are some exceptions. So again, at that point, you can look at the spec, but to get a general idea of how pattern matching works, this idea of looking at the pattern and see if it can generate the subject is a very good first approach. So let's look at what some patterns look like. And essentially, for each pattern on the left column over here, there will be a condition that must be satisfied for the pattern to match, which is described here in the middle, and I describe it in Python most of the time. And there's also some data extraction that the pattern may end up doing, which is described on the right, or in many cases there's no extraction done at all. So if I use something like a number or a string as a pattern, essentially that matches if the object which is subject, which I've over here, is equal to the constant value, the literal value that I'm using here. This one on top is called a literal pattern. And for some special values like true, false, and none, and that's the whole list, comparison is done using the is operator rather than equality, because that's the proper way to compare these, the one that makes more sense. So these patterns are very simple. There's essentially some sort of equality comparison with no data structure extraction. And you can even use, rather than specific literals, some constants like this. But we will go back to this one in a second. Oh, okay. So where was I? I was showing you some of these simpler patterns. So these two are a bit of a comparison. Let me jump on this a bit later. So if you use a single variable name, like x, as a pattern, and matches against a given subject, a variable can always generate any kind of value if you set it to the value that you're comparing against. So essentially, a variable like this always matches. And what it will do as extraction, it will extract the object that you're matching against. We'll see that there's a special case where you want to always match, because it's essentially a way of saying, I don't care what this value is. But you don't care about comparing the object. In that case, you can just use a single underscore, which is a special name. Again, always matches, but it doesn't extract information because it means I don't care. It's what we call the wildcard. I show you some constants at the beginning. There's just equality comparison, and if you have a constant like this one, it can work as an equality comparison, but there are some ambiguities that you have to be careful with, because if your constant is, for example, if you import the secant from OS as a global name and don't have the OS dot, this looks exactly like a variable name. So you'll end up in this case over here, and you don't want that to happen. So this matching requires that your constants has at least one dot in its name to work as this comparison. And other pattern, other simple pattern that you can have is this using a type name with the parentheses, and the parentheses has a key element here that make this a class pattern. And it's essentially checking that your object is an instance of a given class. So you'll see that these are relatively simple patterns. Simple patterns not necessarily meaning easy, but they don't have a lot of parts inside, of moving parts. So let's look at some complex patterns instead, which are composed with typically some other components or other patterns. So what you have in these top two examples look quite similar to the list unpacking that we did, and actually it's an extension of the list unpacking syntax. And the list unpacking is actually not necessarily restricted to lists, but any kind of sequence. And the same way that you can assign in Python using parentheses, brackets, or actually or just comma-separated values on the left as an assignment. In patterns to assign sequences, you can either use parentheses or brackets or comma-separated values. Just notice that if you're using parentheses, you need a trailing comma, same as in a tuple. So the rules are similar to regular Python syntax. So if you have a pattern like this, and you can change this for square brackets, and its round brackets or square brackets are identical in this case. So this pattern will match if your object is a sequence and it has two elements, because my pattern has two elements. And it also requires that every element inside the pattern matches the corresponding element within the list. So essentially, your patterns can be nested and have other patterns inside. So essentially, this 1, 2, 3, 1 is one of the constant patterns that I mentioned before. So that checks that, and this is matched against the first element of my object. So this is comparing the first element of my object with 123. And this pattern is matched against the second element of my object. And this will always match, so it doesn't add a condition, but it adds some information extraction over here. So this essentially will get the second element in this list, which is index 1, into A. Yes, someone is pointing me to a bug in this slide, so thank you about that. I'll get to it when I cover it, but thank you, Simon. So this other pattern essentially matches any list with at least two elements, and this star can be a sequence from 0 to infinite elements long. So this says that the first element must match this pattern, which checks that the value is an int. And this element, which is the last one, so it should be -1 here, as someone is correcting me, should also be an int because it has to match this pattern. And again, I need a sequence of at least 2 elements. And this star mid will capture everything which is not the first and the last element inside this mid variable. So I'm doing a lot of things at the same time with very compact notation. And this, it's relatively to see how this generates lists would have an integer on both ends and anything in the middle. And that's exactly what this pattern matches. It matches lists that start with an int, end with an int, and have anything in the middle. So given that I use a variable name here, it will capture that middle part into a variable. You can also do something similar with mappings. This looks like a dictionary, but again, this works with any kind of mapping. And this essentially checks that the keys name and age are inside the dictionary that I'm matching against. So this is the condition for this pattern to match. And you see that this is slightly weaker. Dictionaries, and this is based on how dictionaries are normally used. In dictionaries, you normally don't care if the dictionary has additional keys. So I'm not checking that if object has a third key, which is favorite color. I don't care if it's there. The pattern will match anyway, as long as the mapping has a name and an age. And whatever is inside those respective keys will get matched inside these inner patterns. In this case, I use just variables. So I'm capturing N and A. But I could use an underscore if I just want to check that the key is present, but I don't care about extracting the value. Or I could say str parentheses parentheses if I want to check that the value is a string. Or I can even do nested things as deeply as I want. There are some minor restrictions about how you can nest and combine things, because some situations are impossible to decide or solve. For example, when generating a list, you normally can put two variables with star in the middle. But in patterns, you cannot add 2 things with a star, because it will be impossible to decide where the first group starts and when the second one starts, because they can be, if you have 10 elements in the middle, they can be 5 and 5, or 0 and 10, or 2 and 8, and it's impossible to decide. So those ambiguous cases are not supported. And again, for simplicity of implementations in this kind of mapping patterns, the keys need to be something relatively fixed, like a literal or a constant or something like that. You cannot put arbitrary patterns on the key side. You can put arbitrary patterns on the value side. So this allows you to essentially, what I'm looking here is what's the shape of this dictionary. Is this a dictionary with a name and age? This is the question I'm asking about the shape. Is this a list starting and ending with an int? Is this a pair starting one with 123? And at the same time, besides asking the question, I'm saying, okay, and if it is, what I want is this second number that I don't know what it is, I want to capture it to a variable, or I want to capture the middle values into a variable, or the corresponding values for these keys into variables. So as I was telling you, this vertical bar essentially it can be read as or, one pattern on the other. You can separate multiple patterns with it. It matches is if any of the patterns match. So in this case, it matches if the object is either 200 or 404 or 500. So it should be roughly equivalent to this code. And then you have this as, this is called the as pattern, and it essentially allows you to use any pattern on the left, and it matches if the pattern on the left matches. But it also captures, if it matches, the whole thing into a variable. So this is a way where I can write, I want a list where the first element is a Boolean or the strings yes and no. And whatever it was, I want to capture it into the variable called flag. And you can see that I'm using star underscore, which means, and this list can have as many elements as you want. And I don't care about those, so I don't need to capture those. So this will check that the object is sequenced, that this length is actually bigger than 1. There's another bug in this slide. And the first element is either or yes or no. Type really quickly and it shows. And it's a Boolean or yes or no. And it will capture as flag the first element, because this as flag ensures that the first element, that whatever is matching here, will also get captured into this variable. So you can convert any kind of pattern in a pattern that captures values, adding as and a variable name. And you can do a lot of combinations of this. For example, you can use this OR pattern to capture different variables. And this pattern is quite interesting because you see that it will always match, because the X on the right will always match anything. So if it tries these 3 different patterns, the third one will always be correct. And what it will do also, it will capture whatever value is needed. So this will always match, but it will still capture, let's say that I'm getting from some weird, very loose API, a value that can be either wrapped in a list or wrapped in a dictionary that has a value, or just a straight away value. So with this, I can essentially say, okay, if it comes, if I get a list with a single element, I'll get the value there. If I get a dictionary with the value key, I'll get the value there. And otherwise, I'll get the whole value. And I'll get one of these depending on the shape of my object. So people are telling me, with the first example, why doesn't extract obj equals this? And essentially, it's likely that you have the subset around, so you don't need to extract the whole thing. But when you have this additional pattern inside something else, like this pipe, you can use this as extra thing to match it. And this as can work with any pattern, not just with your patterns, but with anything, any pattern you can add as at the end as variable, and then add an extra variable capture. So the last collection of patterns that you'll find are the class patterns. And class patterns are essentially an extension of what you see at the beginning, where we are changing a type, but you can essentially pattern match the value of certain specific attributes. So this essentially say, this object will match if it's dark with the color of green, which is what it says here. And this one will match if it's a dark with the color greenish and an H attribute. And by the way, I will want to attribute into A. And again, this could be a much more complicated pattern. So if I want to, for example, capture the H pattern, the H attribute only if it's an int, say int as A, and combine that and add some extra checking. And you can nest them as much as you want. So I want a DAG whose BAM is also a DAG, and I want to extract the H of that BAM. So you can see that with these very simple expressions, you can do things that would normally take you of code to write the check, and also do the extraction of a variable that you're likely to need right away. So, something before we call this. So in this case, I'm using always keyword patterns to pick up the attributes. There are actually there's actually one of those magic Dunder protocol called Dunder match _args that you can define in your objects if you want them to support positional matching. And in this case, you define essentially which positions correspond to which attributes. And some of the built-ins and standard library classes will support this straight away on the release or on the alpha if you download it. For example, name tuples and data classes have the more or less obvious assignment of positional arguments to the positional name of the attributes. And if you look at this, something important to see when you see this pattern in the code is that this is not creating an object. This looks like an object creation, but again, the same as when we have the list on the equal side of an equal sign, and it doesn't create a list actually. this is not creating a DAG. This is defining what kind of DAGs I want to capture. So let's put it all together and see how these patterns look inside our code. And to put all together, I need to show you what's called the match case statement, or some people call it the match statement. Essentially, it's an overpowered if statement, which looks like this. You say match and the given subject, and this will be your obj in the examples above. And you can have several case blocks inside your match statement. Each case will have a pattern and a code block, and potentially a guard with an if label on the left. I will tell you in a second what this. These guard essentially allow you to arbitrary Boolean expressions when you want to add more complex logic. And essentially, the goal of this code is to choose the right code block to execute, similar to an if statement. And at most, one block of code will be executed. So for a block to execute, the pattern must match the subject. The guard must be true. So the patterns are checked top to bottom. The pattern one is checked first. If it matches, this code runs, and that's all of it. If it fails, this pattern is matched. Let's say if match, then the guard is checked. And if both are successful, the code runs. If any is unsuccessful, you go to the third pattern, and so on and so on. If you fall back through the bottom, this code does nothing. It's like an if statement where the condition is false. So when the pattern is matched, the variables that are trying to capture are also assigned. So you can use these variables inside the guard to check complicated things. You can also, of course, use the variables that are matched inside the code block, and that's typically when you need to use them. So let's write a real example of this. Let's write what's called, I call this function my slicer. And I want a funky API, which is somewhat similar to the range function in Python, where I essentially am setting a start, stop, and step arguments, but I want the start and step arguments to be optional. So if I pass only a single argument, this is supposed to be the end of a slice that I'm taking. And if I pass both, I'm taking both. And if I pass 3, I'm taking a slice like this. So this is a simple wrapper to extracting a slice from a sequence. And the only thing weird is about how I'm taking these arguments, which is identical to what the range built-in function does. So if I try to write this with my first idea, I say, okay, I'll make the start and step arguments optional. And this breaks because I cannot put an argument, a mandatory argument after an optional argument in Python, and this will give you a syntax error. So at this point, I say, oh, okay, so what I need to do is take an arbitrary number of arguments or allow the false or null and do a lot of checking on this argument to see what they are. So this seems like a perfect job for pattern matching. So our slicer takes star args, and I'll match these arguments that I got, and I want to know what is the shape of these args. Is it just a stop value? Then I return this. Is it a start and stop value? Then I return this. And is it a triple of these values? Then I return this. And also I can say case underscores. This will always match if none of the above matched. I say, okay, then there was something wrong with the arguments, and I raise a type error. So this is very clean, straightforward. And if we look at the spec, which I've shown in the previous slide with these arrow keys, and this was like our abstract spec, you'll see that our code looks essentially the same that our spec. I just changing the arrow keys with return. But other than that, this is essentially typing our pseudocode inside Python, which is a nice thing and the part that we like about Python. So I'll go through some other quick examples. I don't know how we are on time, so I don't want to overrun, given our delays. So with no coding sample is complete if you don't do fizbus. So that's the problem where you have to print numbers 1 to 100, but replace multiples of 3 with fizz, multiples of 5 with bus, and multiple of both with fizbus. So I essentially can loop on the numbers from 1 to 100. And essentially, if you look at this seems to match over two things. This is actually matching on a tuple, but it's perfectly valid syntax in Python. So the two things that I'm matching are the divisibility by 3 and divisibility by 5. And if it's divisible by both, I print fizbus. If it's divisible by only 3, and I don't care about this one, so I can use underscore, I'll use fizz. If it's divisible by 5, I write bus. And in any other case, I'll print I. Note that I can start using this don't care rather than being explicit at the bottom, because I'm sorting my cases from more specific to more general, and that's the way you normally should do it. So the specific cases match first because they're on the top, and if then you have some files that capture more general scenarios. And as you can see, you can say that match supports actually matching on multiple objects. That's not actually true. It's a tuple, but you can use it as matching on multiple objects, and it works the way you imagine it would, which is quite nice and useful in many cases. So Alexander is asking me, looking at the slicer example, it's a great question, so I'll stop for it. Slicer example of pseudocode, what's the reason behind not super syntax where overloading function signatures are used for pattern matching, like in the pseudocode? And that actually would be great. That sounds like a cool idea. It was something I could tell you about how this feature was designed is that the way we built it, it was already a big change and quite controversial. So we tried to do the minimal thing that makes sense and is useful. You can always add more features like the one you're mentioning later on. But this is a way of getting something that works and getting the community to try it and run it. So it's possible that in the future, one might find how to put this into function definitions. And actually, Tobias, which is one of the authors, says that pattern matching is actually a way of writing function definitions, and everything else is like a secret special case of that, and it's a way to view it that's interesting. But still, putting it in function definitions is complicated because function definitions is one of the most complex parts of Python syntax, and there are a lot of things that you can break around there. So for a matter of being conservative with the change, it wasn't done on the first iteration. Maybe done in the future, or it may be never done because you have to figure out how to create a syntax that integrates properly with the existing syntax. So thank you. I love that question. Thank you, Alexander. So this was our fixed example. Again, this is a very common example. You get a JSON object for an API, and you want to check if it's you have different shapes of JSON to represent different things or different scenarios that you want to cover. Let's say I'm making a login screen, so I get the user info, and if the user doesn't exist, it's an error. And I want to greet the user on his or her birthday. And then if I get the user, and the user is a nested object with the date of birth, which is D, and D is a birthday, then this should probably have some complex logic that removing the year and checking today's date. So here you can see a guard where I can add more complicated conditions. The next page that says happy day, and otherwise rare welcome page. And if I have something which doesn't look like an error or a user, there's something very wrong with the API, and I'll raise an exception. So I will answer Daniel's question later because I want to cover some more stuff. So the other way you can do this is, let's say, okay, a lot of people have wanted a switch statement for a very long time in Python. There were a few rejected PEPs. We finally have it. So match is our thermonuclear switch statement because it does so many more things than switch. But it can also do some of the switch basics, like matching with specific values. And you can insert in the middle. If I get status quo between 500 and 699, just adding an if condition, I can raise a server error and otherwise not do this. In this case, where you're essentially not using the capture feature and just matching like this, I would say that you're trying to write an if statement using the match syntax. So you may decide that it's not worth it to use the match statement for this. And the if statement is a perfectly good statement. Python developers have been using it for decades, and 95% of them have answered to service saying that they are very happy with how the if statement works. So it's still a good choice. Consider using it if match isn't adding anything new. So there are some other use cases that may be around. If you see PEP 636, you can see example of simple parsers, not like full-fledged parsers, but things like more like a command line interface or argument parsing or things like that. And to walk through recursive structures, I have a very complicated example here that you can take a look at. I'll share the slides later on. So you can look at this example, and this is the implementation of red-black tree. And red-black tree is a complicated algorithms where if certain pieces of your tree look in a certain shape with certain colors, nodes have color. If there's a black node on top of a red node and the ankle of the red node is also black and conditions like that, you have to switch this around. And I converted the regular algorithm from an algorithms book, the CLRS, classical CLRS Introduction to Algorithms, into pattern matching, and it's so much cleaner and so much easier to read which are the patterns that you're looking at. So for essentially identifying shapes inside recursive structures, particularly trees, but other recursive like linked lists or things like that, I think it works right. So I'll stop here to answer a few questions. I don't have much more anyway. So people asking me, why is there no else clause in the case statement? And that's a great question, and we've struggled with this for quite a bit. There are a couple of reasons. The first one is that case underscore works, and we can always add else later if we want. So we didn't need it right away. And again, we try to keep the design minimalist. Every time people wanted to add an else clause, there was a weird confusion. Some people wanted to add it like at this level next to the other case statement, because the code that you're doing here is comparable to the code at this level. Some people say, no, the else should go on the left, aligned to the match statement, same as an if-else statement, because all those statements have the else at the same level of the main part. So there was a 50-50 split, and it was easier to not add it because we actually didn't need it, than to get all those people to agree with each other. So thank you for the question, Daniel. So someone's asking me, is there a way of calling the match function as a function without using the match case syntax? I can see this being useful inside building logic apps. The only way to use patterns right now in the match statement at this point. Possibly in the future, it can change. So there are some philosophical points that I want to cover very, very quickly. Most of the idea of pattern matching comes from functional programming, and Python is a very object-oriented programming. But it has a lot of functional programming elements. So it's interesting to see how they fit each other. And it allows you to follow a somewhat different programming paradigm. So in functional programming and with pattern matching, you have essentially dumb values and smart functions. Essentially, the value doesn't know the logic to do one thing or the other, and the logic is outside in your functions. So your functions are probably built with match statements to recognize the different kind of objects. And that allows you to decouple the object representation with the possible variants, which there are some scenarios where you have this very limited set of actions, and you want to be able to add different, let's say, verbs and nouns. So you have a limited set of verbs, and you want to be able to add nouns to your system. And that's very easy in the OOP paradigm, where you just add subclasses that implement the same methods, which are the verbs. So the classes are the nouns, and the methods are the verbs. When you have a relatively fixed number of nouns, but you want to add a lot of different verbs, for example, in trees, you have either nodes or leaves, and those are or two different options. But you want to do a lot of different operations on trees. Normally, you want to put your functionality outside the object, because otherwise you end up with an object with infinite methods, with a class with infinite methods. So for that scenario, the dump value and smart function makes a lot more sense. So it's the dual to method dispatch. In method dispatch, you decide based on an object which method to call. The type decides. In this case, the pattern decides what to call, and it's outside of the object. And it's somewhat comparable in object-oriented programming. If you want to do this, you can do the visitor pattern, but it's quite cumbersome. You have to define an auxiliary class and a lot of auxiliary methods. And this provides some of the benefits of the visitor pattern with a much less boilerplate and a cleaner syntax. So yes, I recommend you to look at the 3 PEPs, which have different purposes. In this repo from Guido, he has added some code examples of different applications, which are quite interesting. There's an expression evaluator with a parser, which is quite nice, and an expression simplifier. These examples, some of them were written for the first version of the PEP, so they may be slightly outdated, but take a look at those if you like. And that's all I have for today. Thank you for the patience through the breakdowns. So any...
Let's do some clapping. Thank you, Danny. That was super interesting. I really like personally really like this new feature. I think it's super interesting. So I would say let's use just I don't know. Maybe we can reply only one more question, because you were already.
Yes, I've already been answering some of those. So.
So let's. There is some delay, so I will give time. So our next speaker is Yuhis. He's already here, so I can probably bring him to the stage. I'm going to turn off your camera here. Hello, Yuhis. Welcome.
Thank you. Hello.
Welcome. Thank you for being presented in Py.Amsterdam. So I want to repeat what I said earlier, that you can join our Slack using this bit.ly URI. If you want to propose a lightning talk, you can reply to a message that is there. I'm going to give that, to that person the data to join the streaming. Also, please send us some messages on Slack or in the chat to see how is the quality of the audio streaming, etc. Because it's the first time for us using a different platform. I'm watching that in the TV next to me, and it looks super good. But it's also good to have some feedback from the rest. So I don't see questions. So you have someone saying it was good. Cheers, Martin. So yeah, thank you very much, Danny. That was super good.
Thank you very much for the audience. Yes, you can reach me at the Moisset at Twitter if you like, and ask more questions if you. I love to discuss about this, so feel free to reach out.
Cool. Yeah, the Daniel Twitter is this one that you're seeing now in the screen. Okay, so thank you very much. I hope it's not the last time we have you in our meetup, and I hope next time is here in Amsterdam and we can share some drinks and chat. Cool. So.